And then, so it's the unique product property. So unique products. Two unique products. Variation of the first. 3 weakly diffuse, whatever that means. 4 diffuse, whatever that means. 5 locally invariant total order. 6 locally invariant partial order. So I'm not going to give definitions of all these things, but I want to say if you're interested in figuring out what's going on in there, you need to know all of these words in order to understand the literature if you go back prior to certain results. So these two were shown to be equivalent in the early 1980s. So I have the name written down here somewhere. Oh yeah, and I can't say this, somebody else will say it for me. Does anyone know how to pronounce that name? It's not me. Anyway, this is who showed that these are equal. Like I said, I've never heard the name pronounced, so I'm not going to try and mangle it. So this is how they did. And then these 4, these are all equal as well. Right? They define the same class of groups. This is due to Linnell and Morris. So we only need to choose one from here and one from here in order to have a complete discussion of the available properties.
They were shy about pronouncing the name from the experts in the back because they claim that it's not spelled correctly when you transliterate.
Oh, let me just see. Oh, really? Oh, yeah, that's according to my notes. I added an extra N. I don't know if that fixes it.
Now, how do you pronounce it?
Strojnowski.
Okay. Yeah, sorry, I actually copied it down wrong. Yeah. So here we have it, and thank you. You should call me out when I make a mistake, even if it's of that kind, especially if it's of that kind. Okay, so we need to choose one from here and one from here. We're going to focus on this and not 2 unique products, even though the difference is only slight. And I'm going to focus on this locally invariant partial order, which is equivalent to these others if you look in the literature. So in order to motivate the definition, we're about to make something that maybe doesn't seem natural as a definition, but in order to motivate it, let me throw up this conjecture. This is the Kaplansky zero divisor conjecture. And G is torsion free and K a field. Then the group string KG has no zero divisors. And one of the early reasons why left orderability seemed to be something worth talking about is that left orderable groups satisfy this conjecture. So what I want to do is show you that, and then from the proof, sort of say, what were the essential ingredients in order to make that proof work? Because maybe we should keep just those and make definitions based upon those properties that we needed to make the proof work. So let's go through and prove that if G is a LO group, A field, AG has no zero divisors. So let's take 2 elements and multiply them together, like 2 arbitrary elements in here. Yeah.
Remind me what the KG is.
Oh, this KG, this consists of all finite formal sums of the form like Ri, Ei, where the Ri's are coming from K and the Gi's are coming from G.
Like the group ring about with the field.
Yeah. So you're just taking finite formal sums and then you multiply them like polynomials and add them as you expect. Yeah, and this should have no zero divisors. So now what I want to do is take 2 elements of this form that are not zero themselves and multiply them together. So let's do it. So I'll just say, here's how the proof of this proposition would go. So consider the product. So sum Rigi at y equals 1 to n times Si SOS JHJ equals 1 to m, and then this is going to be equal to I won't even bother being too careful with the indices, but some sum of Ri, Sj, G, Hj. Right, multiply like polynomials and you get something like this. And so what I want to do is just say, let's consider all the products that we can get Gi times Hj for different choices of G or H coming from those two sets. So to organize our thoughts, I'll say, since the group is left orderable, we can suppose that, let's say these H's, their indices are, they're indexed so that they're ascending in size. So we suppose that H1 is less than H2, is less than HM. Okay. Now, consider the set of all products. And let's say, this is a subset of G, a left order group, right? So let's take the largest element from the set. So say GH is the largest in this set with respect to some left ordering of G. Okay, well now what I want to observe is because Hj is less than Hm for any J, it's not M, right? So since Hj is less than Hm, or J not equal to M, so we have Gi Hj is less than Gi Hm for all Gi. And what that tells us is that anything of this form where J is not M is not a maximal element in the set S, right? So it has to be that this H is actually Hm. Right. But now let's suppose that there's two products that give this maximal element, right? Like J times Hm and Gi times Hm or something like that. Imagine that happened. So if I'll say if there are two ways of getting GH, the product, like, you know, two different choices of GI and GJ, then we'd have so two different guys, GI not equal to J, but GIHM equals GJ, M equals GH. Right, you see this makes no sense because we're in a group, so we can cancel on the right and find that GI should be GJ. So this doesn't happen. There's not two ways of getting GH as a product in this set. That implies there exists some unique GI0 such that I0 HM equals GH, the maximal guy. But now let's think about what that says in terms of our question here, multiplying these things together and getting some product. We want to know that as long as the two elements we're multiplying together are not zero, that the product is not zero. And we've just figured out that amongst all of the products, GI times HJ, there's one product, because it's biggest, that only happens once. If it only happens once, it can't cancel with anything else, right? As long as there's a non-zero coefficient Ri and Sj corresponding to the biggest guys here and here, then it's not going to cancel. So I'll say the product, the I0 HM, i.e. the maximal one, occurs only once out of all Di times Hj. There's no cancellation in this big sum that I wrote. J I Hj. So this thing can't be zero because of the coefficient of this thing. So what was the essential thing that made this work, right? There's two ways of looking at it. Just to recap exactly what made it work is that there's an order on the group such that I can take a maximal element out of all the products, and then by virtue of being maximal, that thing somehow ended up being the unique way of combining two elements from the finite sets in order to get that specific product. So I want to sort of forget that it's left order and keep only the essential ingredients required to make this proof work. And there's two things that I could keep. I could keep this, which is any two finite sets of elements, there's a unique product, and that keeps the uniqueness of this product and it doesn't cancel. Or if I think that the ordering is important, I could keep that maximal elements with respect to that ordering exist, and so can't cancel with anything else by virtue of being maximal. So let's make those two definitions let's make two definitions that capture those. So first definition is that so suppose A, B, and G are finite, non-empty subsets of G. So I want to say what is a unique product for the pair. So if there exists A in A and B in B, such that A in A prime, B in B prime, sorry, A prime in A, B prime in B, and B prime equals B implies A equals A prime, B equals B prime. This is a fancy way of saying there's only one way to get that product from the two finite sets. So then AB is called a unique product for the pair of finite sets. It's called a unique product. And then I want to say that if all pairs of non-empty finite subsets have unique products, the group is a unique product group, a UP group. So if there exists a unique product for all A, B, where A, B, and G finite non-empty, B is a unique product group. I'll just write UP. That's one, that's keeping one of the things, right? So the other thing I said we could keep was something about there exists maximal elements that are somehow going to end up being unique products by virtue of being maximal. It's the next definition I have to write. So a locally invariant order for G is a partial order. So like transitive irreflexive relation. Partial order of the elements of G, such that I'll give myself some space over here. Not left invariant, but something that looks pretty close to it. Such that for all G, H, and G, with H not equal to the identity, either GH is bigger than G or GH inverse is bigger than G. And then a group admitting such a thing will be called locally invariant orderable, or LIO. So a group with such an order will be called LIO, local invariant orderable. Okay, and so why this? So I can say at least this is going to end up capturing the idea that if you take a finite subset, you take a maximal element, it's going to end up being a unique product whenever you're looking at all the pairs that you get by multiplying two finite sets together. But also, this does look a lot like left invariant, right? Although it's not quite, because if H is not equal to the identity in a left orderable group, then you would have either H is bigger than the identity or H inverse is bigger than the identity, and then one of these would hold by just left multiplying by G, right? But we're not saying left invariant. We're saying just one of these holds. So exercise, this does end up forcing the group to be torsion free. And because of what I just said here, left orderable groups definitely are of these kind with the order that they come with. But there's a lot up in the air still. Like, what's the relationship between these two? Can you find examples that show all the things are different? Yeah, I see two. Tommy first, and then yeah.
So why is this kind of group satisfies the Kaplansky conjecture?
So you can go through the unique product. It satisfies the Kaplansky conjecture exactly because it observes and this one, it satisfies the Kaplansky conjecture because in 2 seconds, I'm going to show that these are unique product groups.
Okay.
Yeah.
Okay.
You mentioned two unique products of the property. Was that introduced for a similar reason with a different Kaplansky conjecture?
So the two unique products was just an observation that in all of the situations where you have unique products, as long as the finite sets you're working with are big enough to allow it, actually you have two unique products for every pair. And so the question was, does just having unique products alone imply two unique products whenever the sets are big enough? By big enough, I mean they have to have at least two elements, these kinds of things, right? And it turns out that, yeah, those are the same. I don't know why that was introduced aside from that observation, though. Maybe there was some inspiration. And I mean, it certainly works that way. If you're looking at left orderable groups and trying to figure out what's the unique product there, well, it's a biggest element or smallest element also works, right? So you have two in those situations as well. So, yeah. Okay. So next, I want to show that being LIO implies being UP. And it sort of should work out that way based upon how I'm pitching these definitions to you, right? I'm saying one of them is preserving the existence of unique products, and the other is preserving the existence of unique products by virtue of maximal elements existing, right? So it sort of sounds like it should work that way, and it does. So in a LIO group, G disorder, if S T are finite non-empty subsets, then a maximal element in ST is a unique product. This is one of those like fiddly things where you choose elements just right and then it happens by magic. So let's make sure I get it right. So choose G in ST maximal. Suppose G is not a unique product, not a UP. So then write it in two ways. So G equals ST, which is S prime T prime, where the S's come from S, T's come from T, and we can assume that T prime is not equal to T, right? Because if T prime and T were equal, then it would force the equality of the others, and we wouldn't be saying anything sensible. So you can assume that these are different. Then so then set H to be equal to T inverse T prime, which is not the identity, because we're saying that these are different. Then I want to look at a couple things. So I want to look at GH, right? This times this, that T and that T inverse cancels. So this is ST prime. So this is in ST. ST. And I want to look at GH inverse. You can also be written like this. And then when I take the inverse, this T prime inverse is going to cancel with that T prime. And so another way of writing this is S prime T is also an ST. Right, but now look at the defining property of a local invariant order. One of those things, GH or GH inverse has to be bigger than G, but G was maximal, and GH and GH inverse are both in ST, so that violates maximality. So at least one of these violating maximality. There you go. So what this means is we've arrived at this. So we have LO, it's contained in LIO, it's contained in UP. And I didn't check that this and this both imply torsion free, but they do. That's like a little exercise, go away and do. So we have that chain. Now the question is, have we actually succeeded in defining anything new? Right? It could be that, you know, these are equal, these are equal, these are, you know, something crazy could be going on. So what I want to do is I want to show what we can't show. Okay, like what the sort of current state of affairs is. So okay, good. So let me give an example. So this is the problem-solve group, if you've seen it before, but the presentation that the trick that I'm doing is oh my goodness, I didn't reference it here and I can't remember the names. Okay, but the trick is not mine. And if you want to know who came up with this trick, ask me afterwards. I'll look it up and get it right. So I apologize. Okay, so here's what you do. Is let me define this group first. So you can look at 3 generators, and they're all going to be maps from R3 to R3. So x plus 1, 1 minus y minus z is what this one does. B, x, y, z. And so minus x, y plus 1, 1 minus z. And then c, x, y, z. This is 1 minus x, minus y, z plus 1. Okay. Now, I'm just going to write down a presentation for the group that comes from playing around with these. It turns out that it's this, where you can eliminate C, since it happens that A, B, C is the identity. So that's the group that we're talking about if you want the concrete description. Or maybe maybe you're comfortable just looking at this and saying like, oh, it's a Weber-Bach group or something like that, because that's actually what really matters for this argument. So here's what I want to say.
Crystallographic group?
Yeah, crystallographic, torsion-free crystallographic group. That's what that was going on. So now, here's the claim that you have to check, which I will not check, and I will leave exercise maybe, I guess. Although I have like a little heuristic case written in my notes that can help guide, is that claim for sufficiently large R bigger than 0. The set S. So this is going to be, I guess I should, yeah, G. This is going to be all the elements of G, such that G of 0, 0, 0 less than R satisfies all S and S. There exists G and G such that GS is an S and the inverse S is an S. So it really is use this action and sort of be clever about your choice of G for a given S, and then just observe that by taking R large, your argument will work. And now I want to show that once you've proven that such an S, oh, I should say S is finite. You can also argue that S is finite by, for instance, looking at the fact that if you look at the subgroup generated by A squared, B squared, and C squared, those are translations by even integers along the coordinate axes. And that subgroup is of index 4. And so we can use the fact that these index 4 elements move things quite far in order to show that this is a finite set. Yeah.
Doesn't this always work if little g is the identity?
Oh, yeah, G not equal to identity. Thank you. Yeah. Okay. There exists G and G, not the identity. Thanks. You know, I did a practice run of this lecture and I got called on the same thing in the practice run, and it still happened now. So good eye. So what I want to say is, suppose that you know these properties of S, it's finite and it has this, and now let's show that that means this group is not LIO. And to do that, of course, we suppose it is. Okay. Then S should have a unique product, which is maximal. A unique product, maximal in S times S. Say it's ST. But now choose G that's not the identity. with the inverse S. Yes, and S. Okay. And there's going to be one little thing I have to fudge at the end, and I know I see it coming, and I'm ready for it. Don't worry. Okay. Is that because I see some people squinting, maybe wondering that this is on the wrong side or something. Okay, watch. So then G inverse ST, EST are both in here, SS. But now here's the line that everybody's going to say, wait. It's okay. We'll say, and at least one of the inverse ST bigger than ST, EST bigger than ST holds. And then contradiction, because this is supposed to be maximal. And now here's the part where you're supposed to say, wait a minute, the element G inverse G, those are supposed to go on this side, not on this side, right? According to the definition I wrote. And I just want to say, yeah, that's true. But it's like similar to left ordered groups where there's a convention whether you want left invariance or right invariance, and it's up to taking inverses. You can have it either way you want. And so if I'm trying to show that this group does not admit a locally invariant order, it happens that if I had used the other definition, it goes more smoothly because of the way functional composition works. And I was hoping you would just let that slide and I would be able to get away with writing this. Okay. I didn't want to do it the other way around. So, I mean, I'm just saying I could have defined it this way from the start, and it's the exact same class of groups. Okay.
Sorry, you wanted it like this way just because like this little claim is easier to prove.
Yeah, it's easier to prove this way around because then you're just thinking about functional composition and stuff like that. And yeah, exactly. And then you just have to use the other definition of LIO for it to work out. But after taking inverses, this is exactly what you had already anyway. Okay, so I want to say, so this group is not LIO because of the claim that hopefully you'll improve in your spare time. I don't know. And it's actually better than that, though. This turns out to not be UP even. I don't have a proof of that I could present here because, for instance, if you look at the paper where it's proved, it says, oh, here's a set of size 14, just compute all 196 products and check. So it's actually not. So I should say this is remark 1. And it just happens this is the best I can do at the blackboard. Remark 2, this technique actually works for all torsion-free crystallographic groups with finite Hölder group. But you can do the exact same thing. This is where I really wish I had the reference written down, and I apologize to the authors who are not here, but send out an amended version. So I'll say works for all beaver with finite holonomy. Actually, you don't even need finite holonomy. There's something slightly more general, but that's the easiest way to say it.
Trivial holonomy?
Sorry, what?
It is non-trivial holonomy?
Yeah. Non-trivial finite.
It doesn't derail you too much, Adam. What is the holonomy of a black group? How do I?
Well, the easiest way to look at it is if you quotient. I think it's just if you quotient by the translation subgroup.
Oh, okay. I see.
I think that's true. Sort of. Yeah, so that's thinking quickly on the spot. So there's a chance I might be wrong, but I think that's right. Okay, means that you go back here. I showed you an example of a group which is torsion free, but not this. And then I said, actually, it ends up being torsion free, but not this. So this containment is proper. But we still don't know anything about this containment or this containment. Okay, so let me tackle this containment right here. And I'm not going to be able to actually provide an example and prove that it works, but I can show you the technique that's used. And to do that, I'm first going to show you the technique that doesn't work. So,
Question: is it easy to see that the promise clause group is CO? I mentioned an example.
oh yeah, it's something really silly where it's lexicographic, where you take a quotient onto the Z mod 2, and then the kernel's left orderable or something like that. Yeah. Yeah, it ends up being yeah, just considering the right map onto Z mod 2, then it just works. So how might we try and make a group which is LIO but not LO? So something we might try to do. So how to get IO, not LO. Something we might try to do is observe that there are certainly locally invariant orders that are not left orders. And then what we might want to try and do is show that local invariant orderability behaves differently with respect to certain standard group theorem constructs than left orderability does. So maybe what we would be able to do is do some amalgams or extensions or something like this, where the property of being LIO is preserved, but LO is not. Okay, and then you would end up with an example. But I just want to say that doesn't work out, because it happens that all the cases that are where the behavior of LIO is known, it just behaves the same way with respect to standard constructions as LO. So if you try and sort of get outside of the class of LO groups by doing that, you don't succeed. And so let me say what I mean a little more carefully. So just say example. There exist, I can't believe I didn't do this yet, but there exist LIOs that are not LOs. So step one to our failed attempt, but it's worth going through just to see what we can learn. And so for example, suppose you
Sorry,
take
here you mean specifically like the specific orders, not just groups.
exactly. I can't show that the group. I'm going to give you an example of a left orderable group that has an LIO on it, locally invariant order, which is not a left order. Okay, that's what I'm going to say. Yeah. So for example, just take A and Q, non-trivial subgroup. And then choose an irrational number. That's just positive so that it's easier for me to do. And then define, we're going to embed this. So F alpha R, which is R, it's positive or equal to 0, and it's minus alpha R if R is less than 0. All right, so what we're doing is we're sort of taking Q and then folding it in half at 0, right? And then scaling the negatives that got folded into the positives by some irrational quantity. Now, this is injective, so it's injective upon restriction to the subgroup A. And you can use it to put a total order on A. So define less than alpha on A Q by A less than alpha B, if and only if alpha of A is less than, now this is the usual ordering of R. Let me check that works. And it's not a left order. That's a little bit of fussing around, but not a left order, but a locally invariant order. So now what I want to say is, now that we know these exist, what if we tried to do that trick I said where, we'll do amalgams or extensions or something in a way that LIO is preserved, but LO is not. And maybe we can, construct something that's outside of the class of LO groups, but in LIO, using things like this at every step. Anyway, that attempt is going to fail. And I'll just say the reason that it fails is because if you have a short exact sequence, like this, a short exact sequence, then K H LIO implies G LIO. It's a lexicographic construction exactly as we saw for LOs. And for free products, and then of course, maybe we could move on to amalgams. That's the hope of something interesting happening really is there, because that's where you can get groups that are not left orderable. And maybe you could start with pieces that are LIO and get something that's LIO but not left orderable. But the fact is, we don't have necessary and sufficient conditions that I know about, at least, that an amalgam of LIO groups would be LIO. And the conditions that we do have in the literature are exactly situations where left orderability would be preserved. So you don't sort of find yourself getting outside of the class of LO groups by doing amalgams of LIO groups. So all these attempts amount to nothing if you're trying to come up with a group that is LIO but not LO. So we just need a totally new technique of producing LIO groups other than applying standard group theoretic constructions. And it has to be something that doesn't necessarily force the result to be LO. Okay, now this is the part where I hope that geometric group theorists get excited. We use actions on delta hyperbolic spaces. It works. So here's what we do. We first start with a really sort of simple lemma. So when I write this, you're just going to say, yeah, well, of course, this is saying nothing. But it's really essential. So group E is LIO if and only if there exists a partially ordered set S less than and a function function E G S such that the image of the function behaves exactly like a locally invariant order is what I want to say. So such that for all G, H, and E, H not equals the identity, either P of GH is bigger than P of G, or P of GH inverse is bigger than P of G. Right, and I'm not even going to prove that. There's nothing to say. It's just use the obvious ordering that you get from this partially ordered set, and that works as a locally invariant ordering on G because you wrote down that it had to. Okay. So now, how can we use delta hyperbolic spaces and this to say something? So first, I'm going to define a couple things that probably a lot of people here know, but just for the sake of me gesturing at them as I walk through the sketch of the proof. I want to say what the Gromov product is. So the Gromov product on X is this. So here X is as a metric space, right? A geodesic metric space. And I want to say that it's X, Y, Z is sort of the defect from this being the defect of the triangle inequality. So X equals D, Z, X, D, X, Y. Right. And then space is delta hyperbolic. If this inequality holds minimum of X, T, Z, E, Y, Z, is delta for all T, X, Y, Z, X. Okay. Now, so that's what it means for a space to be delta hyperbolic. Of course, there's also definitions in terms of thin and slim triangles. And so I just want to recall one of those. A triangle is delta thin if, and then I'll draw the picture. So it is delta thin if, it's probably easier for me to draw the picture than write through the sentence. So if when you sketch the triangle, of course it's hyperbolic, so I bend all the edges inwards like this. You have a P and a Q here. And say this distance is this quantity. So as long as P and Q are closer to this vertex, I have to label my vertices. As long as P and Q are closer to this vertex than that number, their distance should be less than delta. So this thing that I drew here is supposed to have like delta, and then this is even smaller. So this is what it means for triangles to be delta thin. And so So what I want to say is I need a little lemma here. And I want somebody to correct me if they know how to do better. So in a delta hyperbolic space, all triangles are, and what's the best bound I can put here? The best one that I was able to prove myself and find.
As soon as there's a bound, that's enough.
No, it's not. It actually, the delta actually matters in what I'm about to do. I know. So I tried to improve it. If you look at Wikipedia, it says they're all 2 delta thin, but I couldn't find any proof of that. But if you look in Gies's notes, for example, it's 4 delta thin. And so I ran with 4 delta. Yeah, it actually matters here because of the application I'm about to do. I realize in general it doesn't, because all you want to do is say it's hyperbolic, but that's why I'm going through all this, because there's this funny little thing where normally you don't even think about it, but I had to. So now, so if anybody can do better than 4 delta, then you can improve what I'm about to do in my notes. But the best I could do was 4 delta. Here's the lemma that makes it work. And suppose that XD is a delta hyperbolic metric space. Then, one more suppose. And suppose that H is an isometry X such that the distance from X to HX is bigger than 6 delta all X and X. So, you know, it moves things far. Then for all isometries G of X and all X and X, either, so what I'm about to write is going to look really promising, so I'm going to write it up here because it's a big deal. So either it's bigger than G X or okay. Now, I want to say this sort of condition on here that I need is this H moving things more than 6 delta. And the reason I went through all this stuff is because let me tell you where that 6 delta comes from. That comes from 2 times the delta, which makes the space delta hyperbolic, and the thinness of the triangles, which for me was 4 delta was the best I could get. So I added 2 delta plus 4 delta, like 6 delta. But if you could improve this, you know, if you're in a space where you know that the triangles are quite thin and you know the delta over here, then adding 2 times this delta to the thinness of the triangles tells you what H needs to satisfy for this to work out. And that allows you to sort of sharpen the result that I'm about to say, because you won't need such a big translation here for such a big distance. Okay. So hopefully from this you can see kind of exactly what I'm going to do, but I'll spell it out. So this is due to Chiswell. Suppose XD delta hyperbolic G acts on X by isometries and for all H in G, with H not the identity, and for all X and X, distance HX at X bigger than 6 delta. Then G is LIO. And it's exactly that previous lemma where you embed something into an ordered set via a map that exactly encodes what it means to be LIO. So I'll just say, let's see, proof. Fix P and X and define theta R by distance, right? BP G. And then it works because exactly it's lemma. So the challenge is to make groups that act on delta hyperbolic metric spaces that move points really far, but aren't left orderable. And then we'll be able to come up with an example of a group which is not left orderable. So there's a few, I mean, there's a whole bunch of consequences of this that I could start listing off. I'll say one, but not prove it, and then this is the one that I liked. Suppose B is a residually finite word hyperbolic group. G is virtually LIO. I won't prove it, but the idea is that, you know, you pass to a small, you pass to a finite index subgroup and you can guarantee this like moving large distances property. And it's, you know, 1 or 2 paragraphs, but I have 3 minutes, so. Yeah. So that's fantastic. And this also means that the fundamental group of a compact hyperbolic manifold is always virtually LIO. Because, well, you need to know that those things are going to be residually finite. Apparently that all works out. Let me say how you can use this to make an example of a group. I mean, this stuff to make an example of a group, which is LIO, but not LO. So let's just say this. We don't have to get so fancy as passing to, you know, acting on like the geometric realization of the Cayley graph or something like that. If it's a complete hyperbolic manifold, then the fundamental group acts on hyperbolic space, right? And hyperbolic space is delta hyperbolic for some delta. I looked it up. Apparently the optimal delta is log 2. And so then if you can guarantee that the action of this complete the fundamental group of this complete hyperbolic manifold moves things far enough, then you can apply this. And so what is, I mean, hyperbolic manifolds have been studied to death. Surely there's some property that exactly encodes whether or not things are moved far enough, and it's injectivity radius. So what you need to do in order to produce an example of an LIO, not LO group, is find the fundamental group of a complete hyperbolic manifold with sufficiently large injectivity radius, which is not left orderable. And then that does the job. And so I'll just say, Dunfield, there exists a complete hyperbolic 3 manifold with injectivity radius large enough that I1M is LIO, yet I1M is not LO. We just verified by computer. You just sort of start trying to build a positive cone and see if you can't. So in other words, this containment, LO groups contained inside LIO groups.
Is the manifold closed?
What's that?
Is the manifold closed?
Yeah, I think it ends up being like, I went through the construction once. It's something where you take a finite index subgroup of a group that arises from Dane filling along a certain knot. And so, yes. Yeah.
It has to be otherwise it has boundary be totally difficult.
Oh, yeah. Yeah. If it has boundary, then it ends up being something much better than LIO or LO. Okay, so I'm going to end by just saying one thing that I didn't do, and then that'll be that. Is there's one containment that I didn't address, right? And it was this the LIO contained in UP. So I need to give you an example of something that's UP but not LIO to show that that's proper, right? Open question. Such things exist. So it could be that these end up being the same class of groups, but I'm skeptical. But then nobody's managed to come up with anything. And actually, even this example of Nathan Dunfield, that's the only one I know of. I don't think that anybody's constructed infinite families or anything of such groups. But it'd be nice if there was a a way that wasn't just a hard grind with computers to find an example. But that's the state of things as far as I know it.
How about random groups?
Yeah, I don't know. That's the problem. Yeah, I don't know where any of these, like, I don't know what would happen. Yeah. Like where they would fall, you mean? Yeah,
They're eventually finite, hyperbolic, and they are not normal. But you're asking about this equation, right?
yeah, this one. But even, I mean, so you're saying, what about random groups and then this one, this kind of result? I mean, I guess maybe you could come up with something, but I haven't seen it written down. Yeah.
No, but this theory is right. I mean, that's proven that they have the three properties that you need.
Oh, yeah, so they are what, okay, yeah. So random groups will fall into there. Good. But then this is still a mystery. That one I'm sure of. This one, I only know this one example, but you say it's easy to make others. So yeah.
What about lattices in the quaternic hyperbolic space, like explicit property T hyperbolic groups?
Oh, I
Do
see.
you know if they are or not left orderable?
I don't know, but that would be a, yeah. Yeah, good. Right, so once you have this hyperbolic, like these the hyperbolic results, it sounds much easier than I thought. It's good.
So the fact you wanted to have 6 deltas because Dunfield has only a finite list of examples, no? That's
Sorry, what's it?
the reason you care about the 6 delta is because Dunfield has only a finite list of examples.
No, the result of so Delzant's lemma. Delzant's lemma, the reason that I had 6 delta is because it comes from 2 times the delta from delta hyperbolic, and then 1 times the delta from delta thin triangles. And if I'm assuming that the space is delta hyperbolic, the best bound on the thinness of the triangles that I could do myself was 4 delta. But for instance, for if you're looking at hyperbolic space, the best delta for delta hyperbolic is log 2. All right, what I'm going to say. And the best delta for the thinness of the triangles is, I think, log 1 plus root 2. And so in that case, I don't need 6 times this. I need 2 times this plus 1 of those. You see what I mean?
For instance, in the first round position, you can take a finite index subgroup so that the displacement is as large as you want.
Yeah.
The value will not matter here. So maybe for the other example with 3 manifold, you don't have that flexibility. I don't know.
Yeah. If you pass to, like you're saying, if you pass to finite index subgroups, then somehow everything's fine, right?
Yeah. So
Yeah, I agree.
Is there an application where you really need that sharp?
Well, if you want something better than virtual, right?
For instance, for the
Yeah, for
3 manifold example,
this you mean, or for the?
for the 3 manifold example,
Oh, I see what you're saying. But then you would have to show.
can you produce manifold with arbitrarily large indicability ranges?
I don't know. I can't say but I assume so. And then,
And you don't need to.
well, the difficulty then is you have to actually check that it's not left orderable as well.
Yeah, what I meant, arbitrarily large indicabilities and
Not left orderable. Yeah, I imagine you can, but I haven't seen that done. Yeah.
How one does check it's not left orderable?
How does one check? Okay, well, first you solve the word problem. And then what you do is you start trying to build a positive cone by just saying, let's throw some elements in and see if it works. And so what I mean is, you start by assuming some elements are positive. You check all the products to make sure you didn't accidentally include the identity in the semigroup that they generate. And if you're okay, then add some more elements. And if it's still not causing the identity to be contained in the semigroup generated by the collection that you have, add some more elements. And you just keep continuing. And the way the algorithm works is either it'll run forever and you learn nothing, or it stops at some time and spits out a reason why it's not left orderable.
In that vein, you have something of that sort for LIO that will
Well, I don't.
certify a failure of LIO.
Yeah. So what it is it's that set S that I wrote down where you have the property that for all S in S, there exists a G in G, G, this not the identity. Oops. Such that GS and the inverse S or in S. So you have to be able to show that there exists a finite set such that for any element in this set, you can always find a group element that has this property.
Forgive me, what does it say right before the such that? In between the G and the such that, what's written there? I can't see. Sorry about that.
Oh, G, but not the identity. So I'm taking for all elements in the finite set, there has to exist a group element in G, not the identity, such that this holds. And if that holds, then the group is not LIO. And if the group is not LIO, that has to hold. So it's like this is, and then what you can do is you can set up a computer that searches for finite sets like this. And that's exactly the authors I can't remember on the spot. That's what they did.
So failure is the existence of a finite set.
Yes.
With this property.
Yeah. Yeah. This is actually what I'm doing here is, you remember there was a list of weakly diffuse, diffuse, and all these other properties. This is the failure of diffuse or weakly diffuse, one of those two written down. And the fact that they're equivalent means that this is how LIO fails.
So for the crystallographic groups with non-trivial holonomy, are they also potential counterexamples to Kaplansky's unit conjecture in the way that the Promislov group is?
I don't know, but I mean, if I was going to tell somebody to start testing, that's where I would look, because there was success there already. I don't know a reason why they would satisfy it, right?
Okay.
Yeah. Yeah. In fact, well, I mean, actually, I don't know if they have the unique product property or not, like all the general ones. I'm not sure.
What did you say that they
Like they don't have LIO,
don't have LIO? Okay, but they might have.
but they might, yeah. And in fact, there's a few groups like that coming from the literature. For example, the fundamental group of the Weeks manifold is not LIO. You know, it's not LIO.
Yeah.
Does it have the unique product property? Don't know.
But it's virtually LIO.
It is, yeah, yeah.